Okay, thank you everyone for joining us this afternoon. This is Paula with Midland Scientific. I'd like to introduce Marv Kaiser, our speaker for today with Antylia Scientific. Marv graduated from the University of Illinois with a BS degree in analytical chemistry. He has spent much of his career training, marketing, sourcing, selling, and managing electrochemistry and spectroscopy product portfolios. Marv is an experienced speaker and has presented at numerous conferences, including PitCon and AWWA. So I will give it over to Marv. Thank you for joining us.
Thanks, Paul. I appreciate that. As you mentioned, Marv Kaiser, Global Product Manager of Electrochemistry at Antylia Scientific. Thank you for attending today's webinar. I'd like to cover a short overview of the potable water treatment process, some key instruments used in the treatment process, and where and why these instruments are used at certain stages of the treatment process. And unfortunately, the slide deck is not changing. Well, I appear to have some technical difficulties here. I cannot get the slide to change. There we go. Okay, as I mentioned, what I'd like to talk about today is the potable water or drinking water process treatment, specifically water quality testing tied to that treatment process. And I'll start with just kind of a fluff intro. The physical, chemical, and biological characteristics of water must be closely monitored to ensure its suitability for purpose. Although drinking water and wastewater have very different requirements, permit requirements for turbidity, salinity, concentration of contaminants, it still must be managed in line with relevant permits and regulations. Antylia Scientific, aka Old Cold Palmer, and Environmental Express have a wide portfolio of instruments and reagents and consumables for measuring and monitoring water quality. So some of the areas I'd like to touch on and discuss today is pH adjustment, perform EPA compliant pH measurements using Oakton portables, flocculants and coagulants, and tie that to water clarity and turbidity and ion reduction, and how to use the new Oakton portable turbidity meters with easy data transfer to support an audit or analysis. We'll touch on disinfectants, specifically colorimetric measurements, free and total chlorine, confirm concentration or levels of chlorine for process and calibration and reporting purposes. We'll also touch on scale and corrosion inhibitors using colorimetric and ISE instrumentation. So this is just a brief, very basic overview of the potable water treatment process. Again, there's many different types of potable water plants in the US. Depending on the region of the country you're in, they may have some different components. But this is essentially starting with the upper left corner. This is a lake or a reservoir. Your pH and flow is measured coming into the plant. Coagulation or flocculation takes place. Sedimentation will occur in the clarifier. If additional conditioning is required, that is the next step. It'll then travel through a filter bed, finally to disinfection and to an on-site storage. I did want to touch quickly on water hardness, as that's obviously everyone in the country experiences some level of hardness. That's essentially calcium or magnesium salts in the water that are dissolved in the water. And although these are non-toxic, they can become an issue as far as reducing the cleaning efficiencies of your soaps or surfactants, might even stain clothes. But again, this isn't toxic, and there's a lot of different means that you can test water hardness. We offer test strips, simple drop test kits, or color wheel kits, colorimetric analysis, as well as ISEs. Okay, so first let's start with, and I must preface this and say that throughout today's presentation, I will shamelessly plug the Oakton product line. And enough said. So first topic is pH adjustments. The key with pH adjustments is you do not want acidic water flowing through city distribution systems. Not only will it corrode the pipes, but it'll accelerate the possibility of leaching, such as lead or copper, into the water. And then it's in the distribution system that'll be piped to its customers. Generally, the normal natural water source is in between 6 and 8 pH units. Obviously, the treatment process, we'd like the output to be 7 to 7.5, which is neutral, 7 being neutral. There's some typical chemicals that are used. The most common part that I've seen as far as water pH in municipal plants, and I'm talking to specifically in the Midwest, where I visited many water plants, is actually slightly acidic water, and carbonates are used, whether it's sodium or calcium carbonate, are used to raise the pH and reduce the corrosiveness of the water. In some instances, it may be necessary to lower the pH. Dilute mineral acids such as a hydrochloric acid or sulfuric acid are used in that situation. The other key thing I want you to take away from this slide is the EPA compliance requirements. The EPA requires 0.01 resolution, automatic temperature compensation, and at least 3-point calibration capability on the instrument that you're using to measure the pH. Now, I started with the top, our 5 series testers, because this is kind of the low cost entry in an instrument that is EPA compliant for reporting pH values. Our 5 series, typically, I believe the pH 5 is about $112. And here's a shameless plug for the 5 series testers. But you'll see that it qualifies and meets all the 3 stated requirements for EPA compliance for reporting. 0.01 resolution of the instrument, 3 calibration points, and all these instruments have automatic temperature compensation. One of the things I did want to mention is be careful. You can't use the low-cost disposable testers. We offer some great low-cost testers. Our pH 1, for example, is about $60 US, but it doesn't have and doesn't meet the resolution requirement. It's a 0.1 instrument versus a 0.01 instrument. So it makes a big difference. You need those 3 qualifiers to be able to report pH and be in compliance. So next, I wanted to talk about our new 200 series portables. These are a basic user-friendly meter used in industries throughout the world. We offer the 250 and 260 models. They come in the pH millivolt or pH ORP. Conductivity, TDS, salinity, and resistivity are the electrical conductance parameters. DO version, a PC version, which is pH plus all the electrical conductance parameters, and PD, which is pH and dissolved oxygen. Now, you'll notice that 0.01 resolution, it has automatic temperature compensation. It has the 250 model can hold 500 data points, which you scroll through on the instruments. If your regulator requires you to electronically document, then you would have to go with our model 260, which is its sister instrument. It has 1,000 data point memory, and you can download via USB cable. It is GLP compliant with time and date stamp on all the measurements that are taken. It's a small portable meter. It's about 6 inches in length. You can easily hold it in one hand and reach all the buttons. Some of the competition out there has just huge meters that it takes 2 hands to operate. This ergonomic design makes it very easy to operate with one hand. And the outer coating has a rubberized coating. And even after it's dipped in water, it will not slip out of your hands. So a great new addition to the Oakton portfolio. But again, the main point here is if you need to establish an electronic audit trail, the key model would be the model 260, which has 1,000 data points, GLP compliant with time and date stamp. So also I wanted to do a quick review. We actually did the 2 and 300 series webinar last year with Midland, but I did want to touch on the variety and flexibility of the kits that we do offer. pH millivolt model, which I just described. We also offer an EC and a dissolved oxygen, a PC, and a PD. Now, these are all kit formats. You see they come in a plastic kit with the meter, the sensor, and the calibration solutions. That's key. You're ready to take measurements right out of the box. Now, one thing else I wanted to discuss a little bit further was buffers. And we offer our standard Oakton buffer group, which is an ACS or technical grade buffer, which most auditors will accept. But if your auditor is requesting an NIST traceable buffer, then you will have to go with our premium buffer, the Oakton traceable buffer line. Now, the big difference there is there's additional stability testing, dilution testing done on the Oakton traceable. But the key here is it does include an NIST traceable certification. So that's a big deal with some auditors. Some auditors are happy that you have fresh buffers and you're calibrating your pH instruments daily, and that'll meet their requirements. But the key here is talk with your auditor or regulator to make sure that you're in compliance with their pH reporting. And finally, I wanted to talk about some bench tops. So we looked at the testers, our portables, and these are some of our lower cost bench tops. Specifically, I wanted to point out our new 1500 bench top. That meter is, the kit format starts at $545 rather. Very nice large display, display icons for pH slope. It's got our full auto suite, including auto calibration, auto ranging, auto buffer recognition, and automatic temperature compensation, which is key for compliance. The top right is our old Oakton 700. It's a real workhorse. It's been out in the marketplace for nearly 10 years now. Great instruments, very durable, easy to use, very robust. 0.01 resolution, up to 5 calibration points with these guys, EPA compliant for reporting pH values. Now, the one thing I did want to mention is the 1500, you can download your data. It is not GLP compliant in the sense that it doesn't have a time and date stamp, but it will download all your values that are locked in the memory. So next, so we talked about pH adjustment and why that's important to measure pH in potable or drinking water. Let's talk about flocculants and coagulants. This is a key part of the water treatment regimen for most potable water plants. Flocculants are considered long-chain polymers. Again, and I'll talk about water plants that I visited in the Midwest. Coagulants are used much more often. These are chemicals used to neutralize the charge of colloidal impurities and enhance the coagulation of suspended solids across a range of municipal applications involving raw water, wastewater, and pre-wastewater treatment. They're widely used to reduce organic matter, color, turbidity, and microorganism levels. Again, the two most common I run into is ferric chloride and ferric sulfate, but you'll also see alum as well, which is aluminum sulfate. Now, the whole value of either a flocculant or a coagulant is that they will aggregate smaller sediment and other particulates in the water into a flock. And as these flock grows bigger and bigger, they will settle out to the bottom of the clarifying tank. And this clarifies the water tremendously, as well as reduces some of the ionic contaminants that are in the water stream. So with flocculants and coagulants under our belt, let's move on to turbidity. The flocculants and coagulants are used specifically to improve water clarity and reduce some of the ionic contaminants in the water. Turbidity instruments are normally used to check the outlet of a clarifier, check your outlet of your filter bed, and after backwashing your filter bed, they're also used to confirm that the turbidity level is very low. Now, potable water plants are mandated to report and record turbidity every 15 minutes. So it used to be that these are just handwritten down, but as technology improves, now they want an electronic audit trail, and we can certainly provide that with our T100 white light turbidimeter, the instrument that's shown here. Now, I wanted to do a side-by-side comparison to obviously one of the market leaders and probably the best selling portable turbidimeter in the world. Both of these instruments are compliant to EPA method 180.1. That is a white light 90 degrees scattered turbidity measurement. They're both plus or minus 2% of reading. The big difference here, and some of the differences I'll talk about are some of the features of each meter compared against each other. But in this case, I'm showing you the price difference, substantial price difference between our kit and the 2100Q, which is offered at $1755. It's essentially the instrument, and for their kit, you have to pay $2141. Also did want to mention our T100 infrared turbidimeter. This is compliant to ISO 7027. This is used by our European colleagues, and it is the compliant instrument in Europe. It does use an infrared or LED light source, that being a key difference between the white light version and the infrared version. Now, the difference between a white light and an infrared Infrared tend to do better with stained water and higher turbidities, whereas the white light does really well at the low end. And that would be and include measurements at 1 NTU or below, and which most potable water is 1 NTU or below. They're actually probably 0.1. So some of the upgrades to our turbidimeter, the display screen. Our competitor uses a standard LCD display. We use a thin film transistor. The TFT has a much higher quality than a regular LCD and its color. As you can tell, theirs is just a darker color and a light color. We use blue for when you're in the measurement mode and green for when you're in the calibration mode. Another big deal is the power consumption. That's some of the feedback I've heard from some of my customers who do use the 2100Q is that it consumes a lot of batteries. So you're forced to buy the power module and download cable at an additional cost. But if you look at the continuous measurement comparison between the two instruments, 4 or 5 hours on the 2100Q versus 25 hours per charge on the T100 white light. It has a 3.7 volt rechargeable lithium battery that's rechargeable through the USB cable. Next, I wanted to talk about True Read, and also to show the top right corner is a example of the download format for our turbidimeter. The True Read measurement mode allows a couple of things. The Hawk 2100Q takes 12 readings, average them, and displays that average value. With our instrument, you're able to say to pick 5, 10, 15, 20 readings to be averaged or have the raw reading. The reading mode is minimum, maximum, average, and every single measurement is recorded. Zero turbidity error. Some years ago, Hawk removed their 0 NTU calibration point and essentially pinned that point, and there's no way to adjust it. Our instrument uses 0 NTU, or essentially distilled water, as your 0 point, and makes the instrument very good at low end, and the accuracy and repeatability is very good at low end measurements, which the majority of the white light customers are going to use. Next, let's talk about the solutions, because this is key. We talked for pH measurements that your buffers are a key part of being compliant for pH measurements, and the requirements of resolution, 3 calibration points, and automatic temperature compensation. Well, one of the big requirements for turbidity is the standard. There's 2 main solutions that are approved by the EPA, the Formazin polymer standard and the AMCO polymer standard. We use the AMCO standard. It's a biodegradable polymer that doesn't settle out. The stable cal standard will settle out over time. And if anyone who's worked with Formazin, it's fairly nasty. It's an amine-based standard that has the same smell as floor cleaning solvent that you might use to clean your kitchen floor. Big difference here is that the AMCO standard is biodegradable and doesn't settle out. I would still recommend inverting the cuvette with the standard in it just to ensure proper mixing. but it's usually not necessary. So next I wanted to talk about the quick overview of the instruments. Where Hawk does beat us is on the data sets. They can store and download up to 500 data sets. Our capability is 200 data sets. But you take that with, we have a better display, better power performance, more features as far as the different modes the instrument offers, a 2-year warranty versus a 1-year warranty, and a 36% lower kit format price. Means our instrument, the Oakton T100 White Light, is very competitive in the marketplace and is certainly a instrument that would be used in a potable water plant. So we've talked about pH, turbidity. Now I'd like to talk a little bit about disinfectants. Obviously, these are kind of the big three in potable water treatment. Disinfectants are added to your water or wastewater systems to dispose of unwanted microorganisms. So that's bacteria and viral contaminants that can be found in water. It's key to that the water is disinfected to remove these, which obviously can, both bacteria and viral contaminants can be very devastating if they are allowed to multiply. The main form of chemicals is oxidizers. These are used specifically because they oxidize the cell membranes of these bacteria or viruses, causing a loss of structure and leading to cell lysis and death of the cell. So they essentially attack the cell wall of either bacteria or virus, literally causing it to collapse. It has no wall to maintain the structural integrity, and that will kill the bacteria or virus. By far, the most used, again, in the Midwest is hypochlorite, sodium hypochlorite, which is just your normal Clorox bleach. It is at a lower percentage. I think that Clorox is 6 or 8% hypochlorite, whereas a water treatment plant is going to use the much purer 15% version. Sodium hypochlorite is available, and calcium hypochlorite is another good option. Ozone is also used. Now, this is a non-chemical addition. I also listed chlorine dioxide, magnesium permanganate, and chlorine gas. Now, it used to be, when I first started in the business, that you would see so many green tanks at potable water plants, and the chlorine gas is very toxic. If there's ever a leak, it's not good. One good breath of chlorine gas and you're in trouble. 2 breaths and you're really in trouble. But the main, most plants now have been converting to the much safer hypochlorite ion, whether it's sodium or calcium. It's easier to handle, it's easier to store. There just isn't the liability issues when compared to chlorine gas. And whenever you're doing colorimetric measurements, whether you're measuring free chlorine, which is normally a measure of the killing strength of a solution, or total chlorine, which is used more often in wastewater treatment. DPD is the EPA compliant wet chemistry reagent for disinfectant concentrations. DPD is N-diethyl paraphenylene diamine. It's a mouthful. But this is the EPA compliant method for a colorimetric measurement. And I've shown some of the different formats, like the color wheel format. A lot of folks use. It's fairly accurate unless you're colorblind. Then it wouldn't be so good. Then I would use a colorimeter, which is single parameter is kind of on the left there, and on the right is a multi-parameter instrument. It's essentially you take a 10 mil sample of your water, you add a powder pillow or a small foil unit dose of reagent, the DPD. The solution, the water sample turns a color. It's kind of a light pink to magna color, depending on how much free chlorine is in that sample. Now, the darker the color, the higher the chlorine concentration. Next, I'd like to talk about scale and corrosion inhibitors. Wanted to touch on these because, as I mentioned, hardness, that results in scale. That's that white chalky buildup you'll see around your faucet, especially around the aerator or even in the sink itself. That's essentially calcium carbonate. That's the same compound that's in drywall. It's white and very hard. Scale inhibitors are typically surface active, negatively charged polymers. Some common examples of these guys are phosphate esters, phosphoric acid, and solutions of low molecular weight polyic acid. Corrosion inhibitors. Now, we talked initially about the importance of corrosion inhibitors. And when these are used, it's key in older distribution systems to literally coat these insides of these pipes with a passive inhibitor such as orthophosphate, which again is in the Midwest, that's used extensively to coat the inside of these pipes. What that prevents is any type of leaching of metals and other contaminants from the piping itself into your water supply. Now, again, these orthophosphate is a very common test. And again, it's in the color wheel kit format, drop test format, or it can be measured with a colorimeter. Again, using very similar to the free chlorine measurement using DPD. This is an orthophosphate, which is free phosphate. This is 10 mils of water. You add a unit dose of the reagent, the little powder pillow, to it. You let that dissolve. You take the color intensity of that, and the darker the color, the higher the concentration of free phosphate. Then next, I wanted to talk a little bit about, circle back, the importance of using a passive inhibitor like orthophosphate. We probably all remember the Flint water incident in Flint, Michigan. They changed water sources, and I'm not going to speak to the detail of it, but essentially what happened was the water chemistry was slightly different. I don't believe they used a passive inhibitor on their pipe, and the new water started leaching iron and lead contaminants from their existing piping. So that's a big deal. Many of the older, bigger cities have lead laterals from the main water supply line leading up to residences and businesses, and it's very important that as we move forward, they remove these lead pipes and replace them with copper or iron, and reduce that amount of lead poisoning. So unfortunately, in the Flint, Michigan, if you remember seeing that on the news, the water samples that were coming out of the tap were very kind of an orangish, which indicates iron oxides, and opaque. You couldn't even see through it. So it's a very disturbing condition up there. My understanding is they have worked hard to remedy that and provide safe drinking water. The last thing I really wanted to touch on was, one of the components of a filter bed for a potable water plant is they're normally a coarse gravel, a fine gravel, it's sand, and then an activated carbon layer, and then sand on top. This is super effective in removing any of the fines that are left in the water, as well as decolorizing and deodorizing. It'll remove sulfides, that's the egg smell. Hydrogen sulfide is the rotten egg smell you might have smelled in water samples. But activated carbon is used throughout the country in these filter beds, and is really good at knocking down, not only odor, color, but the reduction of metals and free chlorine as well. Now, I included I didn't mention fluoride. Some municipalities add fluoride to their water, and we do offer ISEs or colorimetric options for measuring the amount of fluoride in water that's obviously 1 part per million or less. Also, chloride ISE, nitrate ISE. Now, most of these free ions can be measured either with the ion-specific electrode shown on this slide and a benchtop meter, or they can be measured colorimetrically as well. And again, that's just taking a small water sample and adding the unit dose reagent to it, and letting it dissolve and taking measurement of how intense that color is. So that's what I had to discuss today. Again, I just wanted to touch on a basic overview of the potable water treatment process, give you some insight to some of the key instruments that are used in that key treatment process, and why and where these instruments are used and why they're used. So I'll open it up for any questions at this point, and or comments.
One question that came through here says, how do I know when my probe needs to be replaced?
Okay, if we're talking specifically about pH or ORP, that's pretty straightforward, but a good question. For example, on our portables, the 250, 260, and our benchtops, the 1500, for example, they will have an icon on the display which shows an electrode, and it'll have multiple segments on it. So normally the rule of thumb is if you are 100 to 90% of slope, that's an excellent electrode. If it drops to 80, you're getting near some instability. If it drops down to 70% of slope, you either need to, if it's a refillable electrode, empty the old electrolyte out, flush it out with distilled water, and replace it with fresh electrolyte. Most of the electrodes that we offer are a silver chloride reference electrode, and the electrolyte that's used is potassium chloride, either a 3.8 or a 4 molar potassium chloride. Now, let's say, for example, you're using a tester, just a bare bones or pH1 tester. It's a $60 tester. Now, that doesn't have a slope indicator on it, but when you start to see instability in the measurement, and it takes longer, and there is bouncing or drifting in the calibration process. So when the little tester is brand new, you go into the 7 buffer, always start with the 7 buffer. That's 0 output for the electrode. That's always your starting point, and then go into 4 and 10 after that. But what you'll become familiar with the time that it takes for the auto buffer recognition to work. So, and a brand new tester, for example, or a pH electrode, you're going to go bink, bink, bink right to the value. Now, if that value is jumping around, and I mean bouncing around, it reads 4, it reads 8, it reads 6, it's all over the place. You've probably got a coated glass bulb or a clogged liquid junction. Every pH sensor has a liquid junction, which allows the electrolyte inside the electrode or tester to come into contact with the water sample. It's a simple salt bridge. If that is broken, you'll see that bouncing effect. It's very easy to recognize. You'll see it. Then I would clean the electrode, soak it in warm tap water. Do not soak it in distilled water. That will leach the electrolyte right out of the electrode and cause it to be ineffective. So a slow moving pH value, a drifting pH value, or that erratic bouncing, those are 3 indicators that you've got an issue with the electrode. Any other questions?
Another question here, are there any new technologies that we need to be aware of?
Yeah, technologies are always improving, and it's interesting that pH, there hasn't been a lot of changes in pH since Dr. Beckman came out with the first pH electrode and meter back in, I think, the 50s. So pH hasn't really changed much. Conductivity has, the sensor quality and stability has improved quite a bit over the years. As far as colorimetric measurements, which would be used for determining your free chlorine concentrations or levels, or your hardness levels, those have improved dramatically over the years. Now with Dr. Hawk developing the unit dose, little powder pillows, little foil packs of reagent, that made it so much easier to do that type of testing. But new technologies in basic potable water measurement, there's not that many new technologies. Obviously, dissolved oxygen is one area. Used to be galvanic sensors and polographic sensors were the number one sensor technology. Now it's transitioning to optical dissolved oxygen and BOD sensors. They're very fast, very stable, very repeatable. But as far as new technologies on the horizon, I'm not aware of that many. I would mention that a lot of the potable water plants are going to automation. As I mentioned on the that overview of a typical potable water plant, their treatment process, a lot of that is becoming automated with process analyzers. The inflow to a plant is they'll measure pH, they'll measure flow. Obviously, you can't let the flow exceed a certain amount, or you'll overcome the capacity of the treatment plant, which would be bad. But pH, for example, so if a plant has a process analyzer with a pH electrode monitoring their incoming water's pH, a lot of time those are calibrated against a portable or a benchtop unit. So while automation is, I don't know if you'd consider that a new technology, but it's certainly becoming the wave of the future, that these process analyzers are being used more and more often. Any other questions?
If there's no other questions, well, thank you, Marv, for the presentation, and thank you all for joining. We will be sending out the recording of this webinar along with the slide deck for anyone who missed it or wants to review. So thank you all for the time today and have a good afternoon.